Assalamu alaikum everybody. This is task 4 for embedded system designs. We are going to talk about system on chips and field programmable gate arrays or FPGAs in this task. So basically we are going to talk about these two topics and mostly just we are going to talk about them in general and see what's the difference between these two topics. So first thing, what is a system on chip? With the advances of electronic devices, we started having more and more components moving into the same chip as one single system. So all the components of a system are integrated on a single chip. We can find these examples in many things such as Raspberry Pis and mobile phones. So what is a system on chip? We have different definitions, but all of these above definitions are partially right but not very accurate, because in order to have a system on chip you need to have three things: a chip, software, and integration between the chip and the software. You cannot have a system on chip without having the integration of these three things. So the system on chip should include an embedded processor, an application specific ICs for logics and analog circuitry, and an embedded memory. All of this is integrated using an operating system or a software. So all of these are all combined together to give us what we call a system on chip. The hardware alone is not a system on chip. So what's the difference between a processor on chip and a system on chip? So in a processor in terms of processor, here we have multiple simple and heterogeneous. Here we have few complex and homogeneous processors, means all of them are of the same architecture. In terms of cache, we will have one level and small. Here we have 2 to 3 levels and extensive. Memory is embedded on chip. Here it's very large and off chip, which we call the RAM. Functionality, it's a special purpose, and here it's general purpose, but special purpose nowadays with the advances we are going more towards general purpose. If you see the Raspberry Pi, it can run sort of full processor applications, however with a limited capabilities in terms of processing power. So interconnection here is wide and high bandwidth, often through the cache. The connections are through the cache to memory. Power and cost are both low. You can buy a Raspberry Pi for around 20 riyals. In terms of processor, it's both high, it will consume high power, and the processor price will reach around 100 riyals. Operation, largely standalone operations, and here need other chips to run, so it's many different applications. This is the motherboard of the A4 iPhone. Okay, so you can see this is the system on one chip of IC. As you can see here, here's our processor, the antennas, everything is connected to a one system. So this system on chip is running all the application from one chip. As you can see here, you can see here that we have, this is the processor. Okay, here you can see this is our processor. We will have a main processor, we have a processor for the touch and screen, we have the processors for GPS, for the Wi-Fi, for Bluetooth. All of these, they have separate processors, but all of them are integrated within the same chips. This is our input output devices. As you can see, we have audio, we have the SD card, we have the touch screen, we have the LCD, we have the HD TV, we have the camera, we have all the antennas for the Bluetooth, for the Wi-Fi, for the modem, for the GPS. All of these are considered input output devices. And finally we have our memory, which is our boot ROM, our ROM. All of this is integrated within one system chip. Okay, this is called system on chip. Now system on chip and application specific IC, the difference is in terms of how many weeks you can get the product out. Now if you follow up with the mobile industry, let's say for Apple, they have 2 versions every year. For Samsung, they have 2 versions every year. So you need to have your system getting out very fast. Now if you are going to work for an application specific IC, the work for it will take around 1.5 years, which is around 61 weeks. If you work on a system on chip, your work will mainly take 33 weeks, which is less than 1 year, so you can get more chips faster. As you can see here, we have removed the top level design, the time for top level design, the unit block verification, all of this. We kept the integration and synthesis at the same time. We kept the system verification the same time. We dropped somehow from the DVT time. All of these are dropped, but we kept the main things as the same time. This is in the IC. Now, how is this happening? Basically, let me go back over here. If you are going to get a processor, quite simple. Go for the processor company and get your processor. You want a Wi-Fi, get for the Wi-Fi company. So a system on chip uses other intellectual properties and combine them all together to get one chip. We are not creating everything from scratch. Okay, we are not creating everything from scratch. You know that, let's say, talk about Apple. In iPhones, we get most of the components from Samsung, the screens, and sometimes some of the components are got from Samsung. So it's not like you build everything from scratch. In Samsung, you get the processor from Broadcom, okay, or Qualcomm, different companies. You get different components. You build your system from different intellectual properties. So the idea, you can use these standard designs, reuse the standard designs which are already tested. There is no need for you to go and build everything from scratch. This will help you to shorten down the time. So the idea is, on a system on chip, you need to think about many things: identifying the vendors of the intellectual properties, who's responsible for this intellectual properties, evaluation criteria, comparative evaluation and exercises, choice of core, which cores, what I'm aiming, am I creating a system for high end or medium end, who's going to use my device, what is the processing power, how do I do all of things. These come within the part of the design, part of pre-design, for your system. So this is mainly on system on chips. Some of the drawbacks is the time to market, the exponential fabrication cost, increase of time complexity, and increase of verification. So in order to do that, we design and reuse the systems which are already there in the market. So instead of creating your system again from scratch, you reuse intellectual properties. Of course, intellectual properties اللي هي in Arabic حقوق الملكية. يعني instead of creating everything from scratch, no, let's get the Wi-Fi from one company, let's get from the Bluetooth from one company, let's get the processor from one company. All we have to do is combine all of these together and make them work, put the protocols right, and you have a system on chip which is ready to chip and start selling. You can see this in all the components now. It's very rare to have one company doing something by itself. It's all integration of different components from different companies from different countries. Okay, think about it. You will find this is what we are seeing every day in the market. So the next topic we are going to talk about is field programmable gate arrays, FPGAs. Okay, the FPGAs, sometimes called logic arrays, are basically programmable ICs. Instead of going to the fabrication process, instead of creating an application-specific IC, again, application-specific IC means this IC is only used for that application, which is very expensive. Instead, we create an IC that can be programmed for any function, and at the same time, we can reuse it, reprogram it. This will make the cost very, very, very low. You want to create a system, you can create it on an FPGA and start selling the system on an FPGA instead of creating the application-specific IC, which is very expensive. So first we started with programmable logic, and if you recall, we started with the PLAs in level 2, Comp 2113. We talked about how to create a PLA. Then the PLA is done into a complex programmable logic device where we have PLD, programmable logic device blocks, and start interconnecting all of these things together to create our final system. Now, the programmable logic blocks are called logical elements, LEs. See, this is a logic block, the green ones. The yellow ones are just interconnecting switches between these green blocks. So what you have to do is get the lookup table. What's a lookup table? Lookup table, instead of building the logical function, no, we create a lookup table for that function. Just a decoder that will have the inputs already there, and once we choose something, or a multiplexer, once we choose something, we get the output instead of doing the logical circuit. This is faster. This is faster in terms of time and in terms of frequency. So the special functions of an FPGA are the internal SRAM, embedded multipliers, and DSP block. DSP is digital signal processing blocks, embedded logic analyzers, embedded CPUs, high speeds input outputs up to 10 gigahertz. 10 gigahertz, okay. DRR 1, 2, 3 SDRAMs, and phase-locked loops. Now here is a comparison between processors, FPGAs, and application-specific ICs. Which one is better? Now, again, it depends on your application. Application-specific ICs are not flexible, however, they are fast and power efficient. Processors are very flexible, but they are slow and less power efficient. They consume a lot of power. FPGAs come somewhere in the middle. Here are some applications, and this is an example, which is the Cyclone 2 FPGA IC. These are all explaining that particular IC and how it is interconnected. Here we are talking about the delay. When we want to calculate the frequency of a system, we need to calculate the propagation delay. What is the time needed for the signal to go from here to here? So we need to calculate how much time it's needed, the delay inside the D flip-flop, the delay in the wires, the delay in the OR gate, the delay in the wire, the delay in the AND gate, the delay in the wire, then the delay on the D flip-flop once more. All of these together will give us the total delay. One on the total delay will give you F maximum for any system. This is the design flow for an FPGA, and this is a comparison between FPGAs and application-specific ICs. This is mainly the lecture, mostly it's theory. At the end of this task, you will be having a test for 3 days. It's not a report like the previous tasks, so it's just a test. And if you have any further inquiries, we can have more live discussions regarding this topic. Thank you for listening, and hope to see you soon in the first semester, or you are level 4, so this is our last meeting, hopefully. So hope that you will have a successful life and you graduate with flying grades. Hope to see you all soon and wish you best of luck.